Okay, let's continue. General Chemistry Part 18. Now we finish Part 17 talking about dissociation process. Now in which we talk about ionic compound solid and you dissolve into the aqueous solution, which is water-based solvent, and then the polar molecule of water, and is able to split the cation and anion of ionic compound as a solute into solvent into cation and anion pairs, and then go through the collision between different chemical compounds as reactants, and then under driving force for the natural train or the tendency for form some solid or gas or liquid products. That is chemical reaction. If it's not going that direction, then those cation and anion pairs from different species, different chemical compound will remain in the aqueous solution as free cation and anion pairs submerged in the water solvent, but never form any new compound through the reorganization of the composition of, the change composition from the reactants to new composition of products into the products we are able to obtain from the reaction. Then that we not call them chemical reaction, we call chemical change process. Okay, make this clear. So now, in order to understand this process, we have to understand what water can do to contribute any effort or major effort to this process. So we have to go into the concept called the water molecule self-ionization. Some book call it auto-ionization process. Now water has 2 hydrogen atoms and 1 oxygen atoms. As we learned from electronegativity, and oxygen is 3.5, the value of chi, and hydrogen only 2.1. The difference between these 2 elements is 1.4, right? It is definitely not an ionic compound, nor a covalent compound. It must be considered as a polar covalent. So the compound water, H2O, would be a polar molecule, right? Does that make sense? But how this can happen to make this molecule polar, we have to explain that in the next few minutes. But first we're going to get into the process. So assuming there's a lot of water in water-only solutions. Now remember which one of the problem, I think it's in homework number 7 or number 6. One of the problem out of the homework number 7, I think, I asked everybody to do the calculation of 1 liter, which is 1,000 milliliter of water alone, right? What's the concentration of water, in the molarity of the 1 liter of the water solution? What's the water as solute and the water as solvent? What is the molarity? You figure out 1,000 gram, right? Water is 18 gram per mole. That's a gram formula weight. And you divide into 1,000 gram and flip, and then you find it's 55.555. It's repeating that many number of moles of water molecules in 1 liter of a water solution, water liquid, right? Water liquid. If you consider solution, you consider 1 of those or 2 of those or 55.5, all the solvent as a solid as well. So you can do that. So the concentration for water in 1,000 milliliter or 1 liter of water, liquid water, is 55.55 mole, right? Now, as the experimental results showed, every 500 million water molecule are able to have 1 molecule out of 500 million molecules able to go through a self-ionization process. So every 1 out of 500 million water molecule is going to be dissociated into what? Hydronium and hydroxide cation anion pairs. So what are we going to do this writing a chemical change reaction? Equation is going to be water. Now what's the physical state? Liquid, right? You dissolve in other waters. You just pick the one, another water, now basically two, right? So give us one proton from one of the water, and then make a combination from water and one proton, give a hydronium, 1 plus aqueous cation. It's called a polyatomic cation, right? It's one of the quite important, very important. There are very few important cations as a polyatomic cation. This is one of them, right? And 1 hydroxide, 1 minus aqueous anion, right? This is about what? The total in molarity concept, we haven't reached that yet, right? It's about 10 to minus 7. So the concentration for regular water for hydronium, 1 plus, the concentration use the bracket as the symbol for concentration, is roughly equal 1 times 10 to the minus 7. Right, minus 7 what? Mole per liter. Right. That's the molarity. Now we haven't get that yet, but we're going to get in there in the future. All right. That means how many moles, moles, slash per liter of solution, which is 1 mole in how many moles in 1 liter of solutions. All right, this is 10 to the 7 minus 7. All right, and that's how many. All right, that's concentration of hydronium. Now, right. Now this process, we are able to see the neutral molecular compound H2O were able to produce very limited number, very small, 10 to minus 7, right? Amount of water molecule were able to undergo the self-dissociation process to produce hydronium cation, H3O, 1 plus, and hydroxide, 1 minus anion, cation anion pair, right? Now, what is the other chemicals dissolving water, water as solvent, and any other chemical as a solute, dissolving water? So those chemicals is ionic, so they are able to dissolve and dissociate for form a electrolytes, right? Could be strong electrolytes or weak electrolytes or non-electrolytes at all. But if they completely form cation and anion pair, we are calling them strong electrolytes. The ionic compound dissociate in aqueous solution, become zillions of cations and anions pairs, right? In a water solvent. So what happens? So if any, all right, any ionic compound right, dissolves into the aqueous solution, right? Solvent, aqueous solvent. Dissolve into water, let's say water solvent, into water solvent. To make aqueous solution, right? Aqueous solution, right? The polar nature of water molecule plays a role and important to dissociate ionic compound. Or compounds into cation and anion pairs. Right? Pairs. Now, because why? Because water molecule are polar. Polar. Now, what polar means, the water molecule has one end of the molecule slightly negative, the other end is slightly positive. It shows a polarity, right? It's not very, very strong, but it's polarity on both ends, on either end, to demonstrate the attraction from the positive end, right, towards the negative end of other ions, which is anions, and the negative end of the water molecule is able to attract the positive end of other ionic compound, their negative end, right? So that generates a force, strip, or tear down the ionic compound crystalline structure, get all those atoms with charge, we call ions, cation or anions, off the attraction between themselves, but separate them, and then so that they are able to dissolve and dissociate into, or mix into zillions and zillions of sea of water as solvent, and then they are not going back to their crystalline structure anymore in the aqueous solution, right? Aqueous solution. So, if we understand that, so now let's write this for instance, right? For instance, right? For instance, right? Copper sulfate. Copper sulfate. Copper sulfate, right? CuSO4, right? And let's say solid, right? Solid, all right? Is dissolved, right, into water, right? Then what happened? Then the reaction is, look at this, CuSO4 solid, you drop into the water, right? Drop in the water. And then you put a water molecule on top of it. Then this is ionic compound. The cation is copper cubic 2+, right? And split in the middle right here, and the sulfate is a polyatomic anion, it's a cluster. And one sulfur atom and 4 oxygen atoms are always stuck together in the aqueous solution during regular, normal chemical reaction process. It does not go any further to split into sulfur and oxygen atom or oxygen ions anyway. It will not happen. But if you dissolve this solid ionic compound into the liquid water as solvent, this is solute. Now let's put here solute. Solute. This is solvent. Right, the water, right? Then what will happen is a solution, right? The solution has two has two ions, one cation, one anion, and the cation will be the cubic. 2 plus. Now what is its physical state? Because it's dissolved and dissociated in the water, no longer solid nor liquid, it become aqueous status with physical status will be aqueous. So in the parentheses for AQ. The same token for the sulfate. SO4, 2 minus, also AQ. Now you understand this. Now these two, right, were opposite. Charge was exactly same value but opposite signs. If they come back, we can neutralize, but they are not going back unless you dry off this solution with all the water evaporated off, and then the attraction force between the 2 plus cubic cation and the sulfate anion 2 minus will automatically attract each other to put cubic cation into the crystalline structure of the sulfate, copper 2 sulfate, into the crystal, back to this crystal solid again, unless you evaporate all the water solvent. But this is not going to happen spontaneously, right? You have to do something to make it happen. You add energy to drive off. But in this case, what happened? If you break the bond, right? You break the bond in between the cubic cation and the sulfate anion, right? It's more stable in the solution than as a solid, and so it will release the energy, right? Absorb energy and to break the bond, but then become cation anion, right? Will be more stable in the solution. But if you want to combine them back and will release the energy, you break the bond used to, and then to make them a solid back into the crystalline structure. Now in this case, right, we have of course involved some energy, but we don't know the value, right? We just say delta H in this dissolution reaction also involve energy, either endothermic or exothermic. We find out if we need to study, right? So that's the situation, all right? Now in order to understand how can a water have anything to do with the formation of cation-anion pair in the aqueous physical state, right? We need to understand the polar nature of the water molecule. Now let's see if we are able to introduce. That's number 2. Number 3. Number 3. Polar nature of water molecule. Now why we have to study this? Because we use water as the solvent for aqueous solution, right? It's a big part of the chemical reaction, and it will play even more important role when we come to the later part of chemical reaction involved writing net ion equation, those things, and then the physical state change involved, and you want to cancel this spectator, right, species. You have to match the physical state and the chemical formula, the charge, everything has to be same. Otherwise, they are not identical. You are not considered they are a spectator. You cannot cancel them. So that is so important. Right? Polar nature of water. Right? What is polar nature of water? So what happens to water molecule? H2O, right? H2O has a bent-shaped molecular structure. Now, we need to draw a picture, but everyone knows sometimes you say water H2O, but actually it's 1 oxygen in the middle and 2 hydrogen on either side, and then connect to 1 oxygen by a single bond, right? Now that single bond, what kind of a polarity of the single bond between H and O? We need to find out, right? So what happened? Right? What happened? The single bond between the hydrogen atom and the oxygen atom, let me shorthand it, O-ATOM means oxygen atom, H-ATOM as hydrogen atom, right? And the single bond between these two atoms, now we have two pairs, right? We have two pairs. Right? Two pairs of what? H and O, correct? Right? Two of them, right? Two pairs of. Now, what's the nature of the bond? Right? Single bonds, right? Put S, are polar, covalent. Why? Check the electronegativity value and find the difference between electronegativity of these two elements, hydrogen and oxygen. So what is this? We go by oxygen first. The chi for oxygen minus chi for hydrogen is what? 3.5. Let me make it a little bigger. That's a little small. All right, 3.5. Right, 3.5. What is the value for hydrogen? 2.1, right? 2.1. So the value difference between the electronegativity of these two elements is 1.4. The 1.4, remember that diagram for the ionic nature and the covalent nature of the bonding, and the difference for chi, if you drop it between slightly under 1 or slightly over 2 is called polar covalent, right? So 1.4 fitting right in the middle, consider polar covalent. The bonding between hydrogen and oxygen are covalent, but not 100% like a hydrogen diatomic gas molecule H2. They are identical. None of the hydrogen atoms is stronger than the other, so there's no way for any one of these hydrogen atoms to pull the bonding electron between them towards itself and then let the other one almost like a lost the control of the bonding electron pairs. But they share in the middle, right in the middle. So that's 100% a covalent. That's with 0 for that table, remember that. But here the point was right in the middle, so the polar nature is, it's not strong, but it's moderate, right? So what happens if we are able to draw a picture and then identify why this molecule has a bent shape? A bent shape is a geometry for molecular formula, molecular structure for water molecule without consider the non-bonding electron pair. If you consider non-bonding electron pair, then oxygen has 6 electrons in the N equal to energy level, but only 2 form bonding with 2 hydrogen atoms, and the other 4 electrons out of the 8 electrons from oxygen are not forming bonding, so they pair into 2 with self-spin opposite and get close enough range to stay put as a, we call non-bonding electron pair. Or it's called, it's not called bonding electrons, right? Called non-bonding electrons. And then those electron also has the repulsion towards other electron, so they force the shape of the water molecule instead of straight linear, because oxygen in the middle, 2 hydrogen on both sides. If there's no electron somewhere, and they will form a linear straight line, linear structure, just like a line, straight line 180 degrees apart, right? But since there's a non-bonding electron pairs, and they force the structure of the water molecule to be bent over down. All right, we talk about it just by drawing pictures. All right, so if that's the situation, we understood the bonding nature, the polarity of the HO bond in water is polar covalent, right? Polar covalent. Then what kind of a molecular structure it can result? It results a bent, right? We already said. So if we have the oxygen, now the picture, the oxygen is big. Oxygen is bigger than hydrogen, right? That's oxygen. Oxygen atoms, right? It has how many? 6 electron, covalence electron, not the first 2 in the 1s orbital. The other 6, total is 8, right? So you got a 1 electron contribute to the bonding like along the board, this plan, and it connects to one small little atom called hydrogen. All right, and the other one also has the other electron also has the ability to combine with another hydrogen atom. Now they're supposed to be straight. Now here I deliberately made center of our, like it's kind of bent over with angle, right? What is the angle? 104 degree, 104.5 degree. Now, but then because oxygen got 6 electrons, the first 2 is very close to the nucleus, and then the other 6 will be surrounded outside, form a 6 electron in the 2 n equal 2 energy level, and then the first 2 2s, and the other 4 will be 2p orbitals. But these 4 electrons does not form any bonding with anything else because there's only 2 hydrogen. So you have 2 lone pair electrons. Lone pair electron, we call non-bonding electron. Lone pair electron, non-bonding electron, same thing. So they form a cluster getting close to each other, but they are self-spin opposite. So they don't bother each other very much, but they do force the bonding electron right here. There's 2 bonding electrons, one from a hydrogen, let's put across, and then one from oxygen for the dots down there, form bond, right? Form bond. And then these 2 electrons, and here's 2 more from oxygen, right? Non-bonding or lone pair, we call lone pair. Those 4 electrons, they all net nature, charged, right? And then they repair other electrons or bonding electron pairs. So here you have another, all right, hydrogen electron and another oxygen electron. So they supposed to be straight, but since they have 2 lone pair electron, 4 electron total, are concentrated on the other side, so these straight lines no longer straight, become bent over because these 2 lone pair electrons push these 2 bonding electrons down away from them, so the bonding has an angle. Instead of 180, now it's 104. So the difference between the angle is 104 degrees. Oh my God, this is 104, yeah, 104. 104 degree, or 104.5 degree. I think it's 104.5, put down there, all right? Now, how to understand that? This actually, if you include these 2 lone pair electrons, which is non-bonding electron from the oxygen has 6 electron valent, and then the 2 out of 6 form 2 bonding with a hydrogen, but you want 2 hydrogens, right? So what happens is then these 4 electrons not having any other elements to bond to. So they become a lone pair or non-bonding electron pairs, and then when they're around the nucleus or an atom inside an atom or oxygen, but they do have effect to produce a repulsion force between the electron pair, bonding electron in between. So what happened? Supposed to be straight, but now they have look my body into a water molecule. These 2 hands consider 1 lone pair electron, 2 electrons, 1 lone pair electron, 2 electrons, and cut my head off, and use my torso, consider as oxygen, and my 2 legs, all right, consider as the single bond between oxygen and hydrogen, 1. So let me go this way. All right, now